before I talk about GPI, a 1-minute advertisement, which is I'm very close to having funding from NASA for my participation in the Roman CPP, upon which, receipt of which, we're going to start trying to hire a postdoc. So if there's people who are interested in a postdoctoral position working on analysis of Roman data with a particular view towards validating the error budget and understanding the how the on-orbit performance compares to what we thought it would be 10 years ago, find me. I'm only here today, or send me email. I would love to have Zoom calls and talk about potentials for working with our group. But mostly I'm here to talk about GPI 2. That was actually kind of a nice, I'm kind of happy with the order because it's nice to follow on a science result that reminds us that 6 years after Gemini kicked us off the telescope, not that I'm bitter or anything, we're still producing scientific results out of what was one of the first of the dedicated high contrast imaging systems on the sky. GPI, like all of its siblings, combines an advanced adaptive optics system, a sophisticated coronagraph, a near-infrared integral field spectrograph, and really importantly, a lot of software, which will be a recurring theme to keep all of the bits working together in a smooth and relatively efficient fashion. Without going through the design in detail, I want to talk about the stuff that worked and then the stuff that we're improving for GPI 2. So stuff that worked, we had a very science and systems engineering driven design. There was a contrast error budget when we were designing GPI, God help us, 20 years ago, with a couple of thousand cells worth of components that went into what would drive the final instrument performance. MEMS deformable mirrors, it was a novel and high-risk technology when we decided to go on the sky. We're still the only people to put a 4K MEMS on the sky for good reason. No one would do that after us, very sensibly. But the fact that MEMS worked and allow us to build these compact high-performance systems was a major step forward. Really good optics. That's my one lesson for people designing systems. We put a lot of money into buying the best mirrors we could. Individual GPI OAPs are polished to 1 nanometer RMS. The design minimized non-common path errors, both by design and quality of components and alignment. And that made a huge difference. Yes, you can minimize your you can control your non-common path errors with fancy algorithms. It's nice if they start small in the first place as well, so your fancy algorithms don't have to work as hard. And then finally, the data infrastructure put together by the amazing whole GPI collaboration, that we had the ability in real time to get these pop-ups about potential objects that lead to the reports that Natalie was rereading, that we have a database that graduate students can go back to and re-reduce all 600 stars worth, that we had metadata, which I'll talk about a little, that let us understand what limited the instrument performance in a data mining driven way. Stuff that could have been improved, all right, 4K MEMS, it was okay. It did have a significant number of bad actuators. We paid for 2 foundry runs of 4K MEMS, and we never got one with less than about 5 bad actuators in the circle that we were going to control. The new generation of 2 and 3K MEMS for design balance reasons are much better at that. The wavefront sensor CCD we picked was low risk at the time. It had about 4 electrons read noise. That was good 20 years ago. It's not an EMCCD. That translates into a limit for GPI of 10th magnitude for the faintest star that we could reliably lock onto. The appetizers and Leo stops, Reme Sume's chronograph designs, again, good with the math, primitive math we had 20 years ago. They have about 35% throughput, number of valuable photons that we're missing. And then finally, the strongest strongest predictor of GPI's performance on sky was the atmospheric coherence time, basically how fast the atmospheric turbulence is, where fast seeing is off to the left, the atmosphere changing very quickly, slow seeing is off to the right. That made a large difference in how we performed. We were promised by Gemini that the atmospheric coherence time would be 5 milliseconds. It turned out to be 1 most of the time on the sky. And the AO system running at 1 kilohertz had significant compute delays, so that going from the CCD stare to the CCD read, to the math before you send commands to the deformable mirror, meant we were about 2.3 milliseconds stale every time we corrected. That would be okay if the winds were 10 meters per second and you're operating at 5 millisecond coherence times. This is a map of high-altitude atmospheric turbulence. The circle is Sarah Pachon. You'll notice the jet stream aimed right at the damn mountain. So a lot of the time we were operating on substantially faster seeing than we were designed for. And then finally, GPI's itself internal reliability was extremely good. The AO system has 99% scale updates. It doesn't crash. It self-optimizes. There's no knob you need to turn as an observer to make GPI operate in real time. The Gemini Observatory software had a fundamentally different model of how instruments would work, which resulted in, to use it, you had to click a lot of buttons on the Gemini side. You had to right-click your mouse at exactly the right moment in order to make GPI align and operate itself. As a result of which, it's fiddly, and the Gemini, if you're a Gemini support astronomer and it's 3 in the morning, you could use this single object spectrograph where you just sort of push this and then go back to scrolling the internet, or you could use GPI that required you to make decisions. The Gemini Q tended not to operate GPI very often in a way that hurt the ability of other groups to get their programs executed in a very meaningful way. Nonetheless, it was on the telescope for 6 years. It is the most productive adaptive optic system Gemini has ever had by a large margin. Produced a lot of science results both within our group and within other users. Of course, the flagship was the Gemini exoplanet survey that Natalie mentioned. 6 planets, 4 brown dwarfs, except now 7 planets. But more importantly than the individual planets, one of the first papers that systematically looked at occurrence rate statistics with completeness analysis, with the forward model match filter, with an approach that let us say what our probabilities of detecting planets were so we could constrain planet populations. And although the paper with my name on it in 51 Airy, nice paper, the most impactful result that came out of GPI is Eric Nielsen's paper on occurrence rate statistics, by far. GPI 2. So GPI 2, no longer being allowed on Gemini South, we're moving to Gemini North. We will go from Sarapachan to Mauna Kea. We will change our logo from the adorable Chilean fox to the adorable Hawaiian geese. And more importantly, we'll make a bunch of real upgrades to the instrument. This is not being led by me. This is being led by Jeff Chilcote at Notre Dame, Quinn Konopek at UC San Diego, Dmitry Sharansky at Cornell, and Christiane Marois at HAA. I'm just sort of the curmudgeon on the team. And again, it was driven by a detailed science case. We said, what measurements, I'll say a little bit about them, do we want to do better? What knobs do we improve? And with a goal of being a facility instrument. GPI was never about being a test bed. Our technology is never the exact shiniest, the exact fanciest. There's a Skexeo talk after me. You can't possibly compete with that. The point was, GPI would work and let you do a 600-star survey in a way that was relatively low impact and reliable. A facility instrument that, in principle, everybody in the community could use and get data that they're happy with. So we're taken off the telescope in 2020. The goal is to have second light this year. We may need your help for that, which I'll talk about towards the end. A whole bunch of subsystem upgrades. I'm not going to go through all of them, but everything from the Cal-2 self-coherent camera, which there's a poster on here by Christiane Marois, better wavefront sensors, faster computers, new prisms, etc. Faster computers, GPI 2 is designed to run at, oops, let me go back a slide, excuse me, 2 kilohertz, so that we will have 1.1 millisecond of total compute delay. Simulations indicate, combined with the Mauna Kea atmosphere, that should improve contrast at kind of interesting simulations and typical turbulence by about a factor of 5, not to be sneezed at. EMCCD means that Strel ratios will hang in there down to 12th to 13th magnitude, which opens up a lot of interesting science cases. Next generation coronagraphs, the modern numerically optimized designs people like Emile Poor did, and others, have throughputs of about 65%. And there's a poster here by Nicole Wolf on things like end-to-end simulations through the coronagraph, alignment tolerances for the coronagraph, which are still pretty reasonable, and performance as a function of non-common path error. Spectrograph gets an update too. They're prisms that allow a simultaneous YJHK mode, which is very nice for surveys on faint targets. And then the goal was to fix this little last bit of reliability. So moving the instrument internal library from IDL to Python, sad though I am to see IDL go, and to improve robustness against rare failure states so that it really would reach this one button level of operation, so that if something goes wrong, it could recover from it in the night. Doing the upgrade has been harder than we thought, to be honest. When we got the instrument back in 2022, and long story why it took 2 years to get it back, it needed a lot of work. There's a lot of gunk on the optics. We've had to clear almost every mirror off. There was significant rebuilding. There are mechanisms that no longer worked after sitting in Sarapachan conditions for a couple of years unused. A particular thing that didn't really work anymore, this is our H2RG array in 2014. This is a dark current map and a histogram with the dark current right down where you'd want it at 1/10 of an electron per second. This is the YE2RG in 2025. This is the generation of devices that when they sit on a shelf degrade. It sat on a shelf for a long period of time. The good news is Gemini got us a new H2RG, one of the last ones compatible with what we wanted. So the status now is that the new H2RG is installed, the new prisms are installed, we're finishing the process of cleaning all the optics. The pyramid wavefront sensor, which was built by Quinn Konempaki's group, aligned by Savi Perara, who's here, is operating and has been plopped into the instrument. The new real-time AO system the Hertzberg group has constructed is close to the point where it can close loops on GPI, not quite there. Chronograph masks are all installed. The Cal2 self-coherent camera, which is the thing in the upper right, sort of looking like a spaceship ready to collide with the rest of GPI, is very close to the point where it can collide with GPI sometime later in this year. So the project from a technical standpoint is in good shape. Like a lot of science in 2026, the politics are more complicated. So the Gemini board has decided that they will classify GPI-2 as a visitor or a PI instrument rather than a facility instrument. And we're still understanding what that means, whether there's an operations model that will actually work for us under those conditions. The typical model is that the instrument team would operate the instrument themselves using our own engineering interface. There's advantages to that. That removes the decouple with Gemini software. That also requires a lot of staffing and work, and it's not completely obvious where we're going to get the funding to do it. There would be 3 science modes. Initially, verification and commissioning would be done on a target sample that would be selected by the community with publicly available data, which I think is a really good model. Then our group would carry out 2 large and long programs with a broader community team. Natalie mentioned this, I'm going to mention it again. There'll be a public call for membership in the science team that will do the core LLPs. And then finally, if we can find a model that works, that balances our resources in Gemini, it would be available as a guest observer instrument. The LLPs would focus on 2 core science missions. One, taking advantage of the fact that we can operate fainter to look at the very young stars and the forming planets that people like Laird were talking about. This is the one opportunity to do it in the northern hemisphere. And then second, to push the sensitivity limit on the moving group stars down to the point where we could get to a Jupiter mass or to cold start. So we need help. It would be very valuable to have people sign up for our community survey. Gemini, you know, we all get this from our observatories. People say, oh, exoplanet, high contrast imaging, that's niche science. There are 300 people at this conference. This is not actually niche science. We'd like to have all the names of people who are interested in it so we can say to Gemini, yeah, there's as many people as do this as want to measure galaxy formation history at Z of 1. Let's let GPI stay on the telescope. So fill out the survey if at all possible, and we'll look for people to sign up on white papers. And then secondly, the team that we're going to do the core science with is going to be public. And I will admit out loud we made a mistake by not having a public call for membership in the GPI-1 survey. Our intent is not to, we've learned a lot about how to be better people. Our intent is not to make the same mistakes in 2026. So please, Natalie and Briley are wandering around with nice paper versions of this that you can take home. Look at the QR codes. There'll be mailed announcement to the AAS. We want a bigger team. We want a community, and we want Gemini to recognize we have that community, because all the science that we just saw, amazing science we just saw, should be available to everybody in the northern hemisphere. So let me stop there.
Hi, Miles Lucas, Arizona. After receiving the instrument back at Notre Dame and cleaning all of the optics and stuff, are you re-verifying that all of your wavefront errors are still within your budget?
We want to do the intent is to do end-to-end testing on it, see what laboratory performance is, how it works compared to the original, see if we can calibrate a pyramid sensor as well as we could calibrate a Shack-Hartman sensor. Pyramid sensors are great. We had some clever tricks for the Shack-Hartman. So the intent will be to do end-to-end, time permitting with simulated turbulence, but definitely end-to-end with no turbulence before we ship it.
I will misuse my chair powers to also ask a question. I have been seeing, this already goes like quite a while back, that there were some issues with the secondary mirror of Gemini North. I was wondering what, if you could maybe say something about that.
So for those who aren't familiar with it, the Gemini North secondary mirror has significant print through from the supports. I guess they hold it like this, from the supports that hold the mirror up. We've done simulations to say we could live with that if we had to, that by tweaking the reference centroids around the edge of them and then dropping the worst sub-apertures from the reconstruction, the loop will be stable. It will not get to the performance that we'd like. It's about a factor of 2 impact. Gemini is getting a new secondary, so they put a lot of money into this, because if it's bad for us, it would just hammer the GNAO-GERMOS combination. When that goes on is one of the factors in this kind of phasing of putting GPI on, but we can definitely close the loop. We could definitely do better than we did before, than any Gemini instrument did, even with the bad secondary, but we'll be happy if they put the new secondary on.
I think your question will have to wait for the coffee break. Sorry, we're already over time. Thank you all for the presentation.